Welcome to the second exercise. I'm recording. I seem to be great. So last time we had this simple simulation. Today we are going to see the Lua code that controls various objects. I'm going to use a bit of a different example. I'm going to use a non-mobile robot, specifically an RB140 robot, which is an industrial robotic manipulator. This is a classic articulated style robot with 6 degrees of freedom, which means it has 6 joints it controls. There's one here, there's one here, here, and the final one is here at the roof. Yeah, okay. So I'm just going to open a simulation prepared. I'm going to show you why I have prepared the scene in advance. So these types of robots are used in various examples of work. So putting different objects together for various industries, whether it's electronics, whether it's automotive industry. It really does have a lot of applications, and if you're ever in a robotic, in a manufacturing plant that uses robots, you're going to use something very similar to this one. So the difference between my pre-prepared scene and the existing scene is that I have added something that's called an end effector. End effector is just a tool that's placed in the end of the robot. We don't really need it here. I have just added it for my needs because I was doing some other simulations with this. And I have renamed each individual joint, so you can see that each individual joint is named RB140 joint 1 instead of each of them being named joint. This is so in the Lua script we can actually directly access each individual joint and position it in case we need it. Okay, so we're going to open our scripts. We have our RB40 script here, and let's just quickly go over it. So one thing to know about the RB140 Lua script here, and pretty much any CoppeliaSim Lua script, we are going to have 4 functions. That's syscall init, which is going to serve for like initial setup of variables and getting values and stuff like that. We're going to have syscall cleanup, which is going to, as syscall init gets run at the start, this is going to get run at the end of the simulation, in case we want to, like this extra line that I had here with closing a file, something like that can be performed here. We don't need here, we aren't writing to file or anything. And in addition to that, we have syscall actuation here. That's going to control the actuation, the movement of our robot, its joints, and we have syscall sensing in case we want to actively do some robot sensing. We don't have any non-built-in sensors here, so we don't need that. Okay, I'm not going to go in details regarding this code and how it does certain things, just because it's not necessary. For you, I'm going to show you the necessary parts in more detail. So we're going to initialize two arrays, lists, whatever you want to call them. I don't know what the exact implementation is, with values of -1, with total of 6 elements, joint handles and cyclic. We're going to define QLim as an empty list, and we're going to define n as the number of joints here, that is 6. Let me just, okay, that's better. So then we're going to use for to iterate from the first joint to the last joint. Please note, if you're familiar with other programming languages, Lua, like MATLAB for example, the initial value of array for the access value of the first array isn't 0, it's 1. And we're going to iterate from 1 from the first spot to 6, which is the final spot, with the step of 1 to iterate over all of these joint handles. And in each spot we're going to get object handle IRB140 joint, which something that starts with IRB140 joint and ends with I, a number. So if you look at our scene here, we're going to get IRB140 joint 1 or 2 and 3 and so on. We're going to save that into a joint handle to access it later, and we're going to use this command simulation.set joint position to set a joint handle, a joint with a given handle that we have just obtained to a position of 0. How does that position of 0 look? So the first step in the simulation is going to go into this position, which is essentially 0 for it. Okay. Yeah, this here is 0. Here. So that's the position in which value of each joint is 0 that we have set here. And we are also going to get joint intervals, the joint handle, which are going to define the dimensions, that the lower and the upper dimension of the joint that we can go from 0 to whatever the limit is. Wrist is actually something I don't need here, and then the factor I can get it, I can control it, but I don't really need it here. And we are going to call two collision handles. So just access a collision handle that handles robot collision and the collision handle that handles end effector collision. So we had, this is just a placeholder, but if we had like a actual tool here or something, it could detect that as well. And we're going to set all the initial values of joints to 0. Step of each joint is going to be initially 0 and then set here. This is just done so it takes the upper limit of the joint, the lower limit of the joint, divides it by 100 to basically get a maximum of 100 steps in the simulation for each joint. So, you know, a bigger joint is going to move more than a smaller joint. Or to be more precise, a joint with a wider limit is going to move more than one with a smaller limit. So just to make sure each gets 100 steps, we're going to do this. And this is just printing of values. Do we need it? Not really, remove it. And then we're just going to set the initial value to this and the ending value to this limit, whichever possible. So this might not be 0 position, this might be, yes, this isn't the 0 position, so the 0 positions are this, and this initial position that we get is actually the lower end of the possible joints. So we're going to iterate between the lowest possible, so from one limit of the joint to completely the other limit of the joint. Are we going to do that? Well, we have the lower limit, which is the initial position, and the upper limit. So here in the syscall actuation, we're going to go here, and for each joint we're going to increase its current position for the step we calculated, and then we're going to use this particular command for sim set a joint position of the given joint. We access through joint handle, and we're going to set the position we have just made. One thing to note, I'm just going to remove this for a second. After within your iteration here, it's good advice to have some sort of weight, just so you don't overwhelm the presentation, the simulation. So we have 0.1 simulation weight defined here, and then so this is going to calculate a new joint position. This is going to set it with the final element being that we're going to, at the end of it, check if the next position, so in the next simulation step, is going to be bigger than the end one. So here we're going to add it, here we are going to assign that value, we're just going to check the value to see if it will be bigger than the final position, and if it is, we're going to stop the simulation. So we can see that here we can run it, wait for it to get to the end, and you can see it gets to the final position. Now we have a bit of a problem here, and that is that we have a collision. We have that this robot hits the floor and itself multiple times during the simulation, which is obviously something we don't want. So to avoid that, we're going to use these collision handles we have defined before by simply reading them with read collision and the name of the handle, and we're putting it here. Here as C0 and C1 for the end effector placeholder, and this for the actual robot. And then if each of them is 1, or I have defined it a bit more broadly, if it's bigger than 0, then we're going to stop the simulation. So if we run the simulation now, we can see that collisions are 0, 0, that's fine, and the moment we hit the floor, we're going to see the collisions here. You can see that it didn't stop immediately. That's because this weight isn't big enough. So if we increase this weight, it should stop immediately. It just CoppeliaSim just didn't have time to process this stopping. Okay, we won't waste time here. I'm just still going to keep it 0.1 just for demonstration purposes. The robot won't just detect hitting the floor here, but it can detect hitting other objects as well. So let's add bill, which is going to be here on a bit of the path. We don't need the code anymore. Our sensing and cleanup is empty. You can see that we just stop the simulation if there is a collision. And just to demonstrate it, okay, bill here is going to be walking into the path of our robot, and as soon as the two of them collide, they're going to be colored red, and we're going to stop the simulation. That's as simple as it is, no matter the direction. I managed to miss it. So we can use a dynamic object, we can use a stationary object such as this mannequin, and we can see that I hit it immediately, that as soon as it hits it, it stops the actual simulation. Okay, so that's pretty much it for the second part. This is the basic example of how to use Lua scripting in CoppeliaSim. The main things are to remember are getting and setting various values with suggest position or get object handle. There are a lot of examples and documentation available online, the full user manual and code snippets at CoppeliaSim's website. Things that you will need to use are obviously a for loop which you will use fairly often, and if for detecting various things, and also remember the sim weight to actually put this into your simulations, or they're going to generate some errors, as we saw in this example. And depending on joint positions, or on which type of robot you're working with, you can use your joint positions or set them, and so on and so forth. Which exact commands you're going to be using are going to depend obviously on the type of the robot that you end up using. Something like this DR20 is going to have somewhat different commands, but it's nothing that's actually scary when you get into details of it. This one actually has a lot of low level calculation, but something like our old friend R2D2 is actually much simpler. We just read the sensors and control the velocity of the individual wheels and set values. It's nothing really complex or scary. So we're going to observe that in the next simulations, where we are actually going to build our own robot and finally program it. Okay. Thank you for your attention, and goodbye.